Hello everyone, welcome again in Eng-Man YouTube channel. So in this video, we will continue our fractional flow curve case. And in this series of video, we will talk about the breakthrough analysis. Okay, to be detailed, I want to know what is the water saturation and what is the fractional curve at breakthrough. Okay, and I'll also want to know what is the average water saturation behind the waterfront at breakthrough. Okay, so it's actually very simple, but yeah, maybe we can try a little bit more thorough and a little bit more detailed. Okay, so actually it's very simple. I will show you the simple approach first. So I will make a new sheet. Let's say I call it breakthrough or BT analysis, and then copy and paste like this. And then let's make the scale from 0 to 100. Okay. And then let's make it a little bit bigger. Okay, so the easiest, simplest approach is actually just we will make a line like this. I'm going to make this thicker and let's color it red, and I will squeeze it and then just make a line, okay, starting from the initial water saturation, and then just drag it like this until it touches the fractional flow curve. Okay, so we will draw a straight line tangent from this initial water saturation, okay, and touch, okay, like this, touch the fractional flow curve. So we have tangent line here, okay, and of course we can zoom in like this. Okay, so the simplest way is actually just read the plot, just read the chart. So here I think the two lines meet here in this point. So at this point, this is actually the water saturation and the fractional flow at breakthrough. Okay, so here. Okay, so let's say I can make another line, by the way. Okay, and let's make a horizontal line, and then let's color it black, make it thinner, and then I want to change it to dash line. Okay, so maybe it's around here or maybe there. Okay, no need to be very, very accurate, because at the end of the day, this analysis has uncertainty. Okay, there is no way one there is no way one set of data for relative permeability that you use to construct fractional flow, there is no way it can represent the entire reservoir. So yeah, this analysis has uncertainty. Okay, so yeah, there is actually no practical benefit if you do very detailed analysis like creating, I will show you later. Okay, just drag it like this. Okay, and just read the chart. So the water saturation at breakthrough is actually around 40 something. Okay, and yeah, maybe you can call it 44%. Okay, and the fractional flow is around 81%. Okay, so it's like that. And yeah, if we make a conclusion, okay, yeah, it is okay if you want to show the result of value in with uncertainty, like approximately 44% and approximately 81%. Okay. Yeah, because at the end of the day, we have enormous uncertainties here and there. Okay. So this is the simplest approach first. So at breakthrough. Okay. The water saturation SWBT, or maybe, yeah, SWBT. Okay. Or maybe I will just write it like this. Water saturation at breakthrough, okay, is, maybe we can like this, 43.35%. It's actually a better approach. And then fractional flow at breakthrough, okay, just show like this, it's 80.6%. So here you go, you get that, okay? You get the value just by making a rough tangent line like this, okay? But later I can also show you the more detailed approach and we will compare the result. And the next one is the average water saturation at breakthrough behind the waterfront. So it's like this. It's SW average at breakthrough. So by saying SW average is actually the average water saturation in the reservoir behind the waterfront. Okay. And just right click, sorry, format cell, and just make it subscript. And just read the chart, it's 50%. Okay, so here you go. We have the result using the very simple approach, just make a line like that. Okay, but if you want a more detailed approach, simple, maybe we can copy this one first. PT analysis. Let's call it rigorous approach. It's actually not very rigorous in technical term. It's just, honoring the calculus, the the line equation and something like that. Okay, so I will just delete it and then I will put it there and then like this. Let's make it a little bit bigger and then same thing, 100. Okay, and then we make like this. We have derivative, okay, and merge dfw with respect to the water saturation. Okay, so it's actually, this is derivative, but you can also calculate it like this. So this one minus that one divided by this one minus that one, right? Okay, it's like this. Okay, and the same thing, we can make a line, just borrow like this. Okay, but later we will construct a real line, not with, not with, not with this shape. And if you want to make a line, you need 2 points, right? So let's make it SW, x-axis, FW, y-axis. The first point is actually at initial water saturation, this one, and the fractional flow is of course 0. Okay, and we can also have this, okay, to make a line, but we still don't know, right? We still don't know, right? So we cannot make a line here. okay? But I can borrow, I can make a guess using this, the endpoint here. So let's say I just make a guess. The SW is at 50 and the fractional flow is of course at 1, okay? And of course I can make a line using that. Line. So X like this and Y like that. Okay, and then I can make a line here. Okay, or maybe double click, charge type, combo. No, this one will be line, and yeah, like this, and this will be, yeah, sorry, or maybe slim, easier one, just show the line, solid line. Okay. Okay, so let's do it like this first. Okay, that's better. Okay, so let's make it red maybe. And okay, so we can show the line, the equation there. Okay, right? So the equation, so if I have equation like this, y is mx plus c, right? M is the slope, okay, and c is the intersection or the intercept, sorry. And I want to change it to red as well. And so we get the m and the intercept. Yeah. Okay, so just to make you understand, right? But we can check if we zoom in, do they really touch each other? Yeah, we cannot see with our eyes because we need to go to infinity. We need to go to a very small scale to be certain that uh, they cross each other or not. Okay, but of course we can do the calculation using math, with using calculus, and we can also express this curve by using trend line. Okay, and of course we will use polynomial, and let's check the order, show the display equation on chart and r square as well. So currently, and I will make it like this. Okay, so currently the r square is 0.9998. Okay, let's see if we can improve it. Let's say I'm perfectionist if you want. Okay, so this is the perfect line. Okay, so this is the perfect line, and if you are even more perfectionist, you can expand this number to show the decimal value. Okay, so this good. We have two equations, this one and that one. So when they meet together, the value must be the same. Okay, the value must be the same. I want to change it back to 0. Okay, so good. So when they at this tangent, at this intersection between the two curves, the value between this equation, let me color it that way, and then this equation should be the same. Okay, you can do that on paper to get what is the X value, all right? What is the X value that make this line and that line the same, okay? You can do that on paper and you can do that on Excel, but I will do another thing. Let's plot this, okay, against that. Okay, I will borrow that curve. I delete this one, delete this one. Okay, so delete the regression, just change it like this. Okay, and then just reset. Okay, and just change it to DFW with respect to DSW. Okay, so because we have a curve like this, okay, because we have a curve like this, first we go down, all right, we have a valley there. We, if I'm not mistaken, is concave, all right. Okay, and then we go up and then we go like that. Okay, so we have a turn in point there, and that's exactly the tangent line, the tangent position between the straight line and the curve. Okay, and that happened actually at this point. Okay, at this point. Okay, and we can identify that point, the DFW and DSW, the maximum DFW DSW, which is actually the the maximum derivative. We can easily find that by using, yeah, max DFW DSW. Sorry. Okay, it's, yeah, 0.0042, which is actually, yeah. Okay. Oh, sorry, we make a mistake here in the way we construct the DFW DSW. Okay, because it's actually the logic is like this. So if I go here, actually we can construct many tangent lines. So if I make it, so this is one tangent line, and then we can also make this way the tangent line, and then, right, another tangent line. So you can do that, okay, to touch all the point. But of course, it's not practical to do that. But if you do this way, you will conclude that the touching point between the fractional flow curve and the straight line is actually, it occurs at the highest tangent. Okay, I'm going to show you. So we need to correct this one. It should be, we make it dollar like this, and it's also put dollar like that, and there. Okay, all right. So make sure here you make this as a constant, and also this initial water saturation, because actually we construct, or we make tangent line, straight line starting from that initial point. Okay, And if you check this DFW with respect to DSW versus water saturation, you get that. Okay. And the intersection, the crossing point, the touching point between the fractional flow curve and the tangent line will occur at this highest point. Okay. Which is at water saturation of 43.3%, which is very, very close with this one, right? It's not very close, it's actually it. Okay. So, and we can also find it next, the FWD SW. Okay, and just find it using Excel. Okay, it occurs at this one. Okay, and yep, just like that. So we get the answer already if I copy this one. Okay, so the water saturation at breakthrough, which is actually the same with saying water saturation at front SWF, is actually 43.35%. And we can also, let's say, divided by 100, 43.35%. Okay, and to know the fractional flow curve, which also called fractional flow curve, a fractional flow at front, just take it from that 80.64%, which is pretty much very, very close with the simple guess like that. Okay, and what about water saturation, average water saturation behind the front? Okay, behind the front at breakthrough. Then we need to construct a more detailed line. To get this point, we need to correct this line first. So now, because we already have a true value, I can insert here SW is 43.35 and FW is 0.806. Okay, and I will make it like this, make it bold. Okay, it's raining outside, and I will correct my line. I will delete it first so that it's like this. Okay, so I have the correct straight line. I have the correct tangent line. Okay, and we can also construct we can also show the equation at trend line. Okay, it's linear. Show the display equation on chart and r square. Of course, the r square is 1. Okay, so now we have the correct slope, which is 0.0275, and we have the correct intercept, minus 0.3863. And of course, with that, we can get this water saturation. Okay, of course, the fractional flow here at the top is 1. So now we can just calculate the water saturation, the average water saturation behind the front at breakthrough. I can rewrite the equation like this. So y is actually FW and x is actually water saturation. So it's like this. Okay. So to get S, okay, to calculate the SW, it's very simple. So it's just fractional flow minus intercept, and then everything divided by the slope. Okay, or if you want make it on the left, it's like this. Okay, so you get the water saturation by 1 minus intercept divided by slope. So you get that the water saturation, the average water saturation behind behind the waterfront at breakthrough is 50.41, which is actually very, very close with our guess, our first guess, our simple guess, which is 50%. Okay, and we can extend the straight line. I will delete the equation first, and like this, you get that. And you can remake the trend line, and you will produce the same equation, of course. And if you want, make it bold like that. And yeah, actually, we don't need to construct this, but if you want to really calculate it on paper on using Excel, you will find that at the touching point, at the meeting point between the two curves, the value resulting from this equation will be the same with the value resulting from this equation. Okay, so you have that, and I just want to make a note here. So let's name it SWBT, comma FWBT. And let's make it no fill at this point. And also the outline no fill as well. Okay, so you get that. And also copy, put it there. Okay, right? So you have this at breakthrough condition, the water saturation at breakthrough, which is the same with water saturation at the front, is 43.35%, and the fractional flow at or water cut at breakthrough is actually the same with fractional flow at the front, which is 80.64%, and the average water saturation behind the front at breakthrough is 50.41%. Okay, this is the result if you do the rigorous equation, rigorous approach using derivative, using the line equation, and this is the simple approach. You just draw a line and just make a rough reading based on the chart. Okay, and you can also refer to Tarek Ahmed book, okay, the Reservoir Engineering Handbook, and on the topic about frontal advance and fractional flow, you can see a plot like this. So you see, we have fractional flow curve there, we have the tangent line there, and the meeting point between the tangent line and the fractional flow is this one, producing water cut at front, this one, and this is the water saturation at front, and this is the average water saturation behind the front at breakthrough. Okay, and I can also show you the, wait a minute, I can show you also from Tarek Ahmed book. Okay, copy and paste. Yeah. So according to Tarek Ahmed, SWF is the same with SWBT. FWF, fractional flow at front, is actually the same with fractional flow at breakthrough. But they are the same, they are different from average water saturation behind the front at breakthrough. Okay, so you get that. So just remember, in this analysis, we construct relative permeability using core analysis report. We make fractional flow curve. We get we do breakthrough analysis to get the water saturation at breakthrough, fractional flow at breakthrough, and water saturation, average water saturation behind the front at breakthrough. using simple approach, just draw a line, and a little bit more rigorous approach using derivative and using equation of line to get the same result. The water saturation at front or water saturation at breakthrough, all right, and fractional flow at front and fractional flow at breakthrough. Okay, so I think that's all. I hope you enjoyed the video. I hope this video is useful. Thank you so much for watching and see you again in the next Eng-Man videos. Thank you.